everyone, and welcome to another Flan Talk. Today we have Kartik with us. He's going to tell us about his paper on provable length and compositional generalization. Thank you for being here, and you can take it from here.
Yeah. Thanks everyone for joining. I'm Kartik Ahuja. I work at Fair Paris. So this is a joint work that I did with Amin Mansouri, who is a PhD student at Mila and EPFL. So the talk is going to be about length and compositional generalization. And just to set the format, I mean, you can interrupt with questions if you have, or we can have a longer discussion at the end. Um, and some of the things that I'm going to be talking about today are new results. So they are not yet in the paper, but I plan to have them in the next couple of weeks, maybe, in the paper. So the slides may be still under development, but I'm happy to get any feedback and stuff. Okay, so with that, I'll start. So the question that got me into thinking about this work is this ongoing debate in the community on the spectrum of where do LLMs lie on the spectrum of like extreme memorization to like a very powerful form of generalization. And of course, these two extremes are like still not very easy to define. But let's say when you're memorizing, you're just like repeating things in training data. When you're truly generalizing, you're like figuring out some underlying mechanisms of how to, answer a question, reason, and so on. So to understand this question better, I think the perspective of looking at algorithmic tasks is a useful one. For example, if you train a model to sort an array, then if you train it on arrays of certain lengths and you test it on arrays of longer lengths, and if it continues to work well, that's a good signal that the model has actually figured out how to sort the array. But if it does not, then you kind of know that it has somehow memorized some patterns of sorting that are fixed to that certain sequence length that you trained for. So this is the perspective we are going to be taking. But before I dive into our particular perspective to this problem, I'd like to mention other works, not in detail, just to tell like there have been other works that have been looking at similar problems. So one of them is this work on, it's actually a series of work on physics of language models. It's from Zewan Alandru at Fair and his co-authors. Um, so in this body of work, at least the one that I'm showing on the slide, what they do is they train an LLM to look at, let's say, high school math problems. They curate a data set, and they curate data set quite cleverly in a way that you control for the hardness of the problems, you train with easier problems, and then you test on harder problems, and they show some success in this setting. Then there is this other work where there are authors who are arguing for how they can design tasks where transformers have limits on how they can generalize compositionally. So what I'm trying to get at is there is like a division in the literature that some say that LLMs can do this, some say that LLMs cannot do this, and it's still an ongoing area of study. There are some works that from Sanjeev Arora and Anirudh, which talk about how there may be an emergent behavior at play here. Some other works that tell you that despite the progress that we see on LLMs, the last one that I'm showing here, which is GSM symbolic, it's a cool line of work where they show if your LLM was you had shown a certain performance on this GSM 8K benchmark, which is a math benchmark. If you change the name of variables, then you see a performance drop, which kind of says that the model latches onto something spurious, which is the variable name, the particular name that you choose for the variable in solving the problem. So this is just to say that there is a lot out there, and I will be just talking about a certain specific angle. And the angle that we take is that of length generalization. And what got us started was this work from folks at Apple and Mila, who have this very interesting paper where they formulate something what they call the RASP conjecture, and the idea in this work is that they took a bunch of tasks and were trying to find on what tasks do transformers achieve length generalization and on what tasks they don't. And this is what they came up with. The conjecture here is just a statement of the paper from their paper. So they have three conditions for this conjecture. The first is what is called realizability, where what they're saying is that suppose whatever is your task of interest, that should be exactly representable on the transformer that you're looking at. And the second condition is simplicity. So this is a bit loosely defined, but let's just go with it for now, because it's just an empirical observation that they try to formalize as a conjecture. There is no proof for it. So the second condition is simplicity, where they're saying that that if you can encode your task through a short program in this Raspberry programming language, which I'll talk for a bit in the next slide, then this simplicity condition is satisfied. The third condition is that of diversity, which again, I would not dive too much into, but just interpret this as that your training distribution has to be sufficiently diverse. So these are the three key components that they say that have to be true. And under these conditions, if you were training on such a task that satisfies these conditions, then you're likely that the transformer will be able to generalize to sequences of longer lengths. So when I was reading this work, I thought, okay, so there is something about this conjecture which feels that it doesn't have to be specific to transformers. It could be more general. And also, is there a way we could formalize this all into something which is more formal than this? So now just a bit of details on if just for people of what I mean by the Rasp-L. So Rasp-L, I'm showing a bunch of functions from the Rasp-L language on the left-hand side in the slide, where so the important functions you can think are like the last one, where you are basically doing what the attention does in one layer, the KQV function. And there are these different functions which can do like token-wise operations and so on. So with this subset of functions, if you can encode your task through these subset of functions through a short program, then you would see length generalization. And on the right-hand side in the table, you can see examples of tasks for which they were able to find such a Raspberry program, and also empirically confirm that the transformers that they were training were able to generalize beyond the training lengths. So that's where the length generalization comes in. So you'll train, let's say, on sequences of length 10, but you will then test them on sequences of length 20. And for the tasks on the right side in the table, there was no program that they could find. Maybe like, I mean, of course, that's not a proof that there does not exist one, but it's just like, I think empirically, if you cannot find one, then there is, they also observe empirically that the transformer does not generalize on those tasks. So this is the whole pretext of the work, that we would like to formalize something inspired from this. And now I'll go to the problem setting. If there is any questions, this might be a good moment to just ask, but so far I haven't really said anything that's might beg a question, but just in case. Okay, so let's now move into the problem setting. So the problem setting is going to be very simple. It's going to be a very standard supervised learning problem setting. We are going to have input sequence of length capital T, where you have tokens x1 to xt. And then there is a labeling function f, which takes the sequence and generates the label yt. And as a result, we can generate a sequence of labels as well. So for x1, you will have a label f of x1. For x1, x2, you will have a label y2, which is f of x1, x2, and so on. So in this framing, you can imagine that you can even phrase next token prediction like this, where yt is set to xt plus 1. So this is the basic setup. And what we want to learn is a model H, whose job is to make predictions. And this model H is going to receive the same sequence as input x1 to xt. It's going to output predictions y1 hat up to yt hat, y hat t. And this model H can come from a hypothesis class that we are going to call calligraphic H. So our goal is to search among these models and hope to find a model that can do well and match the predictions of the labeling function, not just in the training, but beyond the training distribution. So that's the first thing we are going to call length generalization. So I think there is a question. I think
Yeah,
I'm not
John
able.
Roski asked, I forgot, did that repeat copy task is RASP-L mean make two copies of the sequence?
I don't remember. I would have to check. I think the copy task. I have to remember. I don't remember the details. Yeah. Okay. So we'll have to look at the paper for the answer to that. I'll move on if there is no question. Or yeah. Okay. So yeah. So if my model H can match the labeling function F on sequences that are longer than ones seen during training, then we would say that you achieve length generalization. And in the slide, you see example where I'm just showing the ones in blue. On top are the training distribution where the maximum length is 3, and you're trying to make predictions on sequences that are longer. And that's basically what the setup is. I again see that there are some discussions in the chat. So is there a question, or is that more of a...
I think they're solving it within the chat themselves. It's not
Okay,
directly.
that's good. That's good. I'm glad. All right. So, and then the other notion that I would be talking about, again, in a very simple way, would be that of compositionality. So let's imagine that there are two tokens, x1 and x2. X1 takes all the values that it can possibly take, all the values between 0 and 1. X2 can take possibly all the values between 0 and 1. So, but imagine that in my training data, I only see the data from this pink region, which is a strict subset of the whole bigger square, bigger unit square that we see. So if I train on this data in the pink region, there is usually we are not guaranteed on how the model performs on the yellow regions. But if our model is able to do well, and in particular match the predictions of the true labeling function on the yellow region, then we say the model achieves compositional generalization. So again, so this is one form of compositionality. Compositionality is a very broad term used in literature. So I want to be very clear that this is just one particular instantiation of what compositionality would look like. Okay. And with these two definitions, we will now move to what the learning framework would look like. We would have the standard expected risk minimization like framework, where you are evaluating the loss of the model against the true prediction YT. And then you're just taking the expectation with respect to the training distribution P, and you're searching for all the models that achieve the minima. And let's call all the solutions to this problem hat of H. So the big blue circle that you see is all the models, and the dark blue circle that you see is the ones that solve this problem. And the pink circle that you see are the ones that are the models that actually generalize beyond the training distribution and work well, let's say for longer lengths or from the compositionality aspect. So one thing that I want to make clear here is that in the rest of the discussion, we will not be dealing with finite sample issues, in the sense that for the training distribution, we will assume that we have infinite data from the training distribution. The reason we are going to do that is because when we are talking about length generalization, the problem does not particularly get easier if you're given more and more data from the same sequence lengths. The problem is continues to be tricky or hard if you are even like trying to sort an array, if the length of the array is, let's say, 10, but you're trying to test it on much longer lengths. So for that reason, in standard and out of distribution generalization frameworks, it's common to assume that you can have as much data as you want from your training distribution, but then at the test time, since the support of the test distribution does not match the support of the training distribution, you'd like to be able to say something about generalization beyond the training distribution. Yeah, so I'm still making sure no question for me, right? That's just the discussion. Okay. So now if I have to just map at a high level what RASP conjecture was stating into some form of a formal condition. So the first condition in the RASP conjecture was of realizability, which said that the task that you're interested in should be representable in the hypothesis class. So we can write that as standard realizability condition where the labeling function lives in the hypothesis class. The second constraint was that of simplicity, which I'm going to think of as some sort of a capacity constraint on the hypothesis class. And the third condition is that of diversity in training distribution, for which I'm just going to still loosely use the word diversity and not say something more because I'm just trying to give intuition as to what we are trying to prove. So under these three constraints, the first one being realizability and the second one being that of capacity constraints, what we are roughly trying to say here is that the models that are going to be able to solve the expected risk minimization framework are going to be matching the models that solve my length generalization, for instance, or the compositional generalization. So if you see what is nice about this claim now is that we have moved away from transformers and now we are making a claim just about a certain hypothesis class. And this starts to mirror what we do in pack learning type setups where we know in pack learning when we say that, okay, I'm dealing with a hypothesis class, it has a bounded complexity, say a finite VC dimension, then we know that this class is learnable. And that type of a claim is usually about finite samples, that if you are given enough samples, you will be able to learn it. Here, the parallel is that if you have capacity constraints, then as long as your training distribution is diverse, you will be able to learn it and generalize beyond the training distribution. So that's the parallel I wanted to draw. Okay. So now let's move to the first part of the talk. So the talk will have two parts. One, in the first part, I'm going to deal with hypothesis classes and I'm going to impose some structure on them. And then in the next half, we're going to talk about more general hypothesis classes with less structure. But then that would require, you would see the cost of doing that would be requiring more diversity constraints. Like the diversity would need will be required naturally to be more and more to achieve length generalization. So let's start with the first most natural, at least to me, the most natural example of a model class that can deal with sequences of arbitrary lengths. So this is deep sets. So deep sets can be written as follows. Here you have two nonlinear functions. The first one operates is phi, which operates on individual tokens like x1, x2, x3 in your sequence, and then just averages them. And then it sends it to the next nonlinearity, which is omega. And this is, you can think of it as like, a deep set kind of a model can be thought of as like a bag of words kind of classifier. So it's permutation invariant, as because you can just send a different order of sequence and you'll still have the same output. So even for this model class, can we try to show the conditions under which we will have length and compositional generalization? So we are going to state the first result. So firstly, I mean, I'll parse the theorem in not a linear way. I'll first say that, okay, realizability condition holds, which is the one that we saw, where that my labeling function is also a deep set of this form. Then the second condition that I'm going to require is that the outer nonlinearity omega is going to be a C1 diffeomorphism. So a C1 diffeomorphism is basically a map which is invertible, and the in both ways, like in the forward direction also it's continuously differentiable, and also in the reverse direction. So basically the inverse is also continuously differentiable, and omega is also continuously differentiable. So it can represent a quite an interesting class of nonlinearities, because you can still warp the space, like the inputs to it, but it also is restricting the expressive power, because you're now not allowing, let's say, the models, the input to the models be any larger than to be living in a space that has a dimensionality any larger than the output space. And the last constraint, which is of the form of diversity, is that we will require that the support of each token is, let's say each token is d-dimensional, then we are going to say that it's going to be, let's say, 0, 1 to the power of t. So each token will have to span the entire hypercube. So under these conditions, and the last condition that we will have at least sequences of length 2 in my training data, we can guarantee that the model that you would learn via the expected risk minimization will match the true function f, the labeling function, in the both length generalization sense and the compositional generalization sense. So h hat will be equal to f on this larger hypercube where the tokens can come from the 0, 1 to the power of td, which basically means that if you go back to this picture that I was showing earlier, x1 was your first token, x2 was your second one. So in this case, the marginal assumption is satisfied that x1's, and for the pink one, the marginal distribution is 0 to 1, and the marginal distribution for x2 is 0 to 1. But now we are guaranteed that the model generalizes to the larger square. So that's our first result. Now let's try to uh, prove it, but I'll just show some of the key steps, but not all of them. So at the first step, what we are going to do is we're going to equate an element that we learn, like the function that we learn, to the true labeling function on the training sequences. So if we do that, we can take the function from the left hand side, the non-linearity, invert it and bring it to the right hand side. And then if we do this just for the sequence length 1, then we get a relationship between the nonlinearity psi, which was being the nonlinear, the embedding that was learned, and the true embedding from for the labeling function. And then the two are related via an bijection A. So now we would like to show certain properties of this bijection A. If we observe carefully, we can see that this bijection A satisfies this property that the summation of this bijection operated over the nonlinearities is equals to the A of the summation of these bijections. So if we could write it in this form, we have basically A times an average of something is equals to the average of A's. So this hints towards linearity. It's not exactly linearity yet, because for linearity, if you remember the basics, the linearity requires two things. It's the additivity property, but there is also the homogeneity property. So the first condition does not imply homogeneity, but we know that our function A is also continuous, which we can exploit. And this is the part that I'm not going to get into. It's just some details that if A is continuous and it satisfies this averaging sort of property, then you can still show that the map A continues to be linear, so that you can think of this as an alternate definition to linearity. So if we now what we have arrived at is the function psi is related to the true mapping phi via linear transform. And this is useful because this holds for all for all tokens in the space. And we can then apply this condition and then take the A outside. And since omega composed A is equals to rho, we get the true labeling function. And if you see this identity that we get, it's independent of the sequence length. So this can be applied to arbitrary sequence lengths, and that's why you get that for deep sets you get this condition. So that's the first result. Now we'll move to transformers, and we are going to do some fair bit of simplifications when dealing with transformers, but in the later half of the talk, you'll see that the results that we have will capture, we'll try to move past these assumptions that we are just going to make right now. So we can also think of, now let's think of a one block of a transformer. So a one block transformer has two key components. One is the attention module, and then there is the MLP. So in this case, the way I'm representing the transformer, you can see that the omega is the MLP that operates on the outputs of attention, where I'm modeling attention as follows. There is this function psi, which looks at my query xi and computes the attention times the value and everything, written as psi of xi xj, and then it averages it. So there is some catch which is here, which I'm going to clarify, but let's just go with the flow. We can compute the query, like just to show how this can capture one type of a transformer. You can see that query is equals to some wq times xi, key is wk times xj, and v is also wv times xj. Then we can compute qi transpose kj and do this times vj and do a sigma. So typically your sigma is a softmax, but here we are doing a different averaging. Here we are not doing the standard softmax type averaging. This can allow you to incorporate nonlinearities like ReLU, but it does not allow you to take a standard softmax type transformer. So you can use this to study like a ReLU based transformer. And there are some empirical works that have studied that ReLU based transformers are also useful, and they work quite well. At least there are some papers that I've seen which have used them, some in the NLP setting, some in the vision setting. And often I've seen this assumption is made to just be able to make the analysis tractable. And that's kind of was the reason we also did that. Um, and so now with this model, you can see that, okay, this is a one block transformer which can express some nonlinearities in attention, but it does not capture softmax. So now with this model, you can see that this model is very close in the spirit to the model that we had for deep sets, but now this allows you to have a pairwise relationship. But I haven't spoken anything about the positional encodings and anything, which also make transformers different, but which I will come to in a bit. So the result here is again very similar to the case of deep sets, where we are going to say that the map omega, if it's a diffeomorphism, a C1 diffeomorphism, and my realizability condition holds, and there is some diversity condition on the tokens, then we know that if the sequence length is greater than or equal to 3, then we basically have again a similar result that we saw in the earlier slide. And the the proof sketch is going to be the same, so I wouldn't repeat that here. So this tells you that gives you some intuition that okay, simple one block transformers can length generalize, but well, these simple one block transformers may not always capture the tasks of that you are interested in. So okay, now one important question that might come to someone's mind is that does this allow you to extend to multiple attention heads? Because a one block transformer could still have multiple attention heads, and that is doable. But I wouldn't talk about how, but it's doable using very similar arguments. About positional encodings, which makes it different. So for positional encodings, what we can do is we can incorporate relative positional encodings, but we will not be allowing for long range interactions. Where by long range, I mean that you cannot go longer than your sequence length. But as long as there are interactions between up to a certain length in your label generation process and your training length is larger than that, then you're good. So you can think of relative positional encodings where you two positions very far do not interact, but like they can interact up to a certain length. And the last one, that should be a very crucial one. Okay, we only expressed one block transformer. What about multiple block of transformer blocks? This is going to come in the later part of the talk. Okay, so far, so good. We have discussed deep sets, we have discussed transformers, and now we are going to look at state space models and RNNs. So if there are some questions, I can pause. If not, then I can move to the next part. Oh, actually, there is one result I want to show about transformers before I go there. So here I'm just showing you an experiment that just to show what's going on here. So let's say you took your one block transformer, and in this case, we actually took a softmax one just to show that, you know, I mean, you can take a non-softmax one also, but if you take a softmax one and you train it up to a sequence's length of 10, then the model that you learn can match the predictions of the trained of the true labeling function for more longer sequence lengths. And here we are dealing with like, you know, each of these non-linearities can have multiple layers, you know. So the hidden layer, the MLP has two blocks, MLP has two hidden layers. That's allowed. It's just that the block as a block, there is only one block. So that's the last thing I want to show on this part, but I can move on if there are no questions. Okay. So now let's look at state space models. So in state space models, we can think of one way of visualizing what happens in a state space model is that there is a linear dynamics in the for the hidden states. represented in a way that's shown here. So you have your token xt, which is combined with which is passed through some linear layer and combined with the previous hidden state to generate my current hidden state, which is passed through a nonlinearity to generate my label yt. So one important aspect that I'm going to say is that this, uh, that here we are now again going to impose certain assumptions on omega and lambda and b, and they are going to have the following form. So again, we are going to think of omega as a C1 diffeomorphism, which is what we have been dealing with. So that part does not change. The matrix B is going to be limited to be a square matrix. So we cannot take our tokens and project them into a higher dimension. So that makes the expressivity limited, but that's what we are dealing with in this setup. And then the last assumption would be that you have your the training sequences of at least length 2. And of course, we still require the realizability condition to hold. So under these conditions, if I generate my data from a state space model which satisfies this assumption, and I learn it via another state space model that is from the same family, then I can match the predictions of the state space model on longer sequence lengths. So there is one important remark that I want to make right now. When I'm matching the true model, it's not necessarily that I'm learning that exact model, which means that the matrix that I learn, let's say lambda tilde and b tilde, they are not necessarily lambda and b. That's also true for the results that I talked about earlier. For instance, if I go back to the results for transformers, when I was saying that the model that you learn matches the true model, the function phi that you learn does not need to be the true function. Those can though there is an equivalence class there. So what that equivalence class for these simple functions that we have been looking at turns out to be that there is a linear relationship between the uh, function psi that you learn and the embedding, the true embedding. Something similar is also going to happen for state space models. That
John,
the hidden,
John Roski asked a question. He asks, if you have a finite hypothesis class, can't you
yes,
just test the previous theorems so that position coding, depth, etc. don't matter?
Sorry. So for finite, I will be coming to finite hypothesis class in a bit, but here these are still infinite hypothesis classes because lambda and b are can still live in a d-dimensional space. But I will. That's a very good question because I'll soon be coming to finite and infinite hypothesis classes, and probably we can see more connections there.
Great, thank you.
Okay. So with this, this is the result for state space models, and let's now quickly look at how the proof sketch looks like here. Again, this won't be all the details, so you can equate the true labeling function and the learned labeling function. You can take the nonlinearity from the left-hand side to the right-hand side. There is a simple way we can show that this relationship between omega inverse rho can be shown to be a linear map. Then we can do some rearrangement from this step to this step and get everything on the left hand side. And using some rank conditions, we can arrive at this equality that each of these terms are 0. And then again, using some simple algebra, we can show that, okay, if this relationship holds for all lengths up to I, this relationship also has to hold for all lengths, like doesn't have to be for just the lengths in the training. And that's the key thing we exploit in showing the generalization beyond the training lengths. So and this also because this gives you a linear relationship between tokens, it also allows you to say that the whole compositional aspect in the same way. So again, I just want to re-emphasize that because we are assuming square matrices, we are limiting the capacity, but still these are still infinite hypothesis classes, which could have a bounded Rademacher complexity, and we are gonna be coming to that part in a bit. And the last thing is that the estimated hidden state that you would have learned by a certain model will be related to the true hidden state in the label generation for the label generating function. That relationship would be linear. So now the last part before I turn to the second half of the talk, which is going to be a bit faster, is so this is on RNNs. So the key difference between RNNs, the result that we are looking at, and the ones that we looked at just now for SSMs is that now we are going to allow for the hidden state to evolve via a non-linear recurrent dynamic. And this sigma that we are going to use is going to be the sigmoid function. And the rest of the story remains the same, except that the omega now is going to be a linear, like up, it's is a single layer perceptron. So with that, the other conditions remain the same, that my matrices A and B, which is being used, and also lambda are all square matrices and they are also invertible. So then again, the result has the same flavor, that you have realizability. You limit the expressivity by limiting the dimensions that the hidden state can take by making these matrices square. If that is true, then we can show that for the R and N as well, you have this length and compositional generalization result. So at this point, you might be tempted to ask whether the result or the proof sketch of this looks similar to the state space models. Actually, that's not the case. The proof of this looks different. And since that it's harder to give all of that intuition in that slides, I don't include it here. But I'm happy to talk about it offline. So this is the result for RNNs. And again, the same intuition that was there for SSMs holds, that you have a linear relationship between the hidden state and the true hidden state. But one important aspect they are different is that now the hidden state and the true state are related by a permutation transform. And that has to do with the sigmoid function. And I wouldn't get into those details. But you can say that there is an equivalence class of RNN solutions that we are basically analyzing here, which are related to each other via permutation matrices. Okay. Now let me turn to the second half of the part of the discussion, which is on general hypothesis classes. And this would be separated into two parts again, which is one on finite hypothesis classes and the other on infinite hypothesis classes. So for finite hypothesis classes, it's quite, and in this half, we are only going to be looking at length generalization. We will not be talking about compositionality because it gets trickier to think about compositionality in the way I defined in these cases. So let's think of length generalization for finite hypothesis classes. So the first condition with finite hypothesis classes is that the set H has a finite cardinality. The realizability condition holds. And what we can show is that there exists a T naught which is finite. As long as my training length is greater than the T naught, then the solution to expected risk minimization achieves length generalization. And this is actually quite easy to show. So the proof goes as follows. Let's look at any possible element inside this hypothesis class H. It can be of two types. One is that it's a good one, where that is the risk of it is zero for all time steps, which means that if you happen to land on this one, you will generalize. And then there is the bad one, which is for this one, there exists a certain time step for which the risk becomes greater than zero. So these are the only two cases that can be true for any function g. So let's define T naught to be the maximum over all these TH that we have defined. And since my set H is finite, T naught is also finite. So what's interesting now is that if my training sequence length exceeds T naught, which is larger than the largest time that it takes to realize that this is a bad guy, because the moment you are going to exceed that time sequence length, that then you can identify that, okay, this is a bad guy in the sense that the risk of this is greater than zero, so it will not be a solution to expected risk minimization. So if you can make your time larger than all the times that are needed to identify all the bad guys, then you basically have the risk that is zero for all the remaining ones, which remains zero for all time steps greater than T naught. So this is a fairly simple result. So what this result tells you is that, okay, it's finite hypothesis from a finite hypothesis class point of view. If your transformer or anything, if you're willing from a length generalization point of view, it says that, okay, if you were to quantize the weights and look at everything in finite precision, and if realizability was to still hold, then you can achieve length generalization provided this T, like, I mean, it could be that this T naught is very high, but But from the definition point of view, that you would be able to now generalize to any sequences longer than T naught. So this shows, it gives you an existence argument that, okay, from a finite hypothesis class point of view, if you discretize everything, things are possible. But then this is again not necessarily true, that when you discretize things, that your labeling function is still in the hypothesis class. So for that, let's turn to infinite hypothesis classes. So for infinite hypothesis classes, what's the key challenge that comes up for infinite hypothesis classes? So we are going to be, so we had the hypothesis class H, which was every element of it was a function that could operate on sequences of arbitrary lengths. Let's try to break down this hypothesis class H into different hypothesis classes, where in, let's say, hypothesis class H1, we look at functions that operate on tokens of fixed dimension, let's say 1. Then H2 is where you have the functions that operate on sequence of length 2. Then H3 is the one that that you operate on sequences of length 3, and so on and so forth. So as a result, you get basically sets of functions, a sequence of sets of functions from t equals to 1 to infinity. So the intuition that we want to build here is that somehow we would like to transfer the argument from the finite hypothesis class case to the infinite hypothesis class case. And to be able to successfully do that, we would like to be able to build a cover. And we would like to build a cover which works for all of these functions in this, all of these sets from H1 to H infinity. And we need to make a certain assumption which allows us to build a bounded cover which works for all of these sets of functions. And the assumption that's shown in the later half of the slide, which I call uniform Lipschitzness, is going to precisely be able to help us do that. So what we are going to assume, let me tell you the assumption first and then give you examples, is that the function h is Lipschitz. And Lipschitz in the parameters theta. So if say theta is the weights of the transformers, or the parameterization of the transformer, and theta prime is another parameterization, as long as these weights are close, my outputs will not diverge and they will always be close, no matter the sequence length. And there will be a fixed Lipschitz constant that works for all sequences. So one just to say that, okay, Lipschitzness is sometimes, like, just to give you an intuition, okay, if your gradients are bounded, or if my function is continuously differentiable over a compact domain, you can then say that, the function is always Lipschitz. But you would like to be to have a fixed Lipschitz constant that works across all the sequence lengths. And that's something I'd like to tell you a bit more about. So if you recall, in the previous slides, we had instantiated transformers via this mapping, omega composed with averaging of the attention. So you can think of the transformer, a multi-block transformer, as a composition of functions of this form, ul minus 1 up to u1, where each u is a composition of an MLP with a nonlinearity. So if my outer nonlinearity omega is Lipschitz, both in the inputs and its, let's say, parameters, and psi, which is the inner nonlinearity, is Lipschitz in the parameters, then the multi-block transformers are uniformly Lipschitz. Then you can show that no matter how the sequence length grow, whatever the sequence length be, since there is this averaging operation, things don't blow up, and you're always have a fixed Lipschitz constant. I wouldn't be deriving it right now. We can also make a claim for multi-block SSMs. So in the previous half of the talk, we had looked at SSMs, but we had looked at only one block SSM. Now we can have multiple blocks composed from UL to U up to U1. And now if the spectral norm of my matrix lambda is less than 1, and my inputs are bounded, and as long as these conditions hold, and my outer nonlinearity omega is Lipschitz both in inputs and parameters, then my multi-block SSMs also are uniformly Lipschitz. And the last one is for RNNs. For RNNs, we have, as you can see, that we have two things, right? We have the inner thing which determines the recurrence that generates the hidden state that is passed to the nonlinearity omega. So as long as the activation sigma is Lipschitz, omega is also Lipschitz, both in inputs and parameters. And I have now a different condition that the spectral norm of lambda times the Lipschitz constant sigma is bounded, like it's less than one, not bounded, it's less than one. Then this class of RNNs are also uniformly Lipschitz. So one thing that I've tried to show is that for these different parameterization of these different functions, you can show that they are all under some conditions uniformly Lipschitz, and it allows you to express all these multi-block models as well. So if this condition holds true, we are basically, in some sense, now we have been able to build a finite cover which works across all sequence lengths. And that is gonna be the key in the main result that I show you in the next slide. But you can think that I'm trying to build this cover because I'm trying to bound the Rademacher complexity. So if I now have my function class H, which is parameterized by theta, and let's say I can build a finite cover for it, which is theta c, which I can because I was dealing with these Lipschitz things. So if my function is uniformly Lipschitz, if realizability condition holds, so you can think that this uniformly Lipschitz is a capacity constraint. F belongs to H is the realizability constraint. And the third one is that there exists a T naught, which is the diversity constraint. And under these three conditions, I'm going to say that an epsilon, an approximate notion of length generalization is possible. And the possibility is that the result is that the risk, like the error for every sequence length, is always going to be bounded above by some epsilon for all time steps. And now comes the last and the most crucial part, that the learner that I'm using is not the standard expected risk minimization learner. The learner that I'm now using is a different one. This one looks at all the, let's say, searches through all the elements in my cover and picks the one that satisfies this condition that the error is less than epsilon for all the training sequence lengths at all time steps. So this is, instead of like a expected risk minimization problem, this is now a constrained minimization problem. And this is very similar in spirit to what group DRO tries to achieve, where you try to minimize the maximum risk of all the groups, where you're trying to ensure that the risk for every group is small. So here, if the times each sequence length was a group, then it's like group DRO in some sense. It's also similar, very similar to the collaborative learning models that are also analyzed in learning theory literature. So this is the last and the main result that I wanted to show, just to give you a quick intuition on from a pictorial point of view. So we have all the models in blue, the models that can length generalize in the small pink circle. And then there is a maroon circle where we are saying that, okay, let's relax the notion of length generalization and say that, okay, then there are a larger set of models that satisfy this. And now instead of searching over all the possible models, we build a cover. And this cover, we have a condition that the cover has to be sufficiently refined, which means that a smaller cover won't do. So it has to be refined so that it captures the solutions that we look at, that we care for. So these two stars end up in this maroon circle. And we operate with the requirement that we are going to try to minimize the risk at time step 1 and time step 2 separately, and try to look at the intersection of the solutions. And that puts more constraints on the problem, and you're able to achieve generalization. So of course, that the thing that I've said, this procedure is not a computationally tractable by any means, but it is showing that, okay, for large hypothesis classes, if we maybe move away from the standard expected risk minimization and go towards more like group DRO type things, maybe there is more hope to build more general learners that have a better chance of achieving length generalization. So with that, I come towards the end, and I just want to show you some quick experiments. So we looked at 4 families of models: deep sets, transformers, state space models, and RNNs. And we do these experiments where we train them with sequence, we generate a data for sequence length of 10, but then we are testing on longer sequence lengths. And for all these, you can see that the scale of the y-axis is very small. It's 10 to the power minus 5 roughly. So the error is still very close to zero. And in the lower half of the slide, what I'm trying to show you is the r square, where r square here being closer to 1 is just corresponding to, we are checking the relationship between the learned representation and the true representation, which is that the outputs of the learned, the embeddings and the true embeddings, is there a linear map between the two? And if that is, if there exists such a map, this number is close to 1. And you can see that in both cases for different sequence lengths, this continues to be the case. And in this last slide, we are also checking for the compositional part, where we, instead of checking for only in the inner region, we are checking the model on the outer parts of that yellow square that I had shown earlier, and the model continues to have a good behavior. So now, to just close, we've developed a first framework that is studying length generalization. Of course, this is just a very first step in this challenging problem, and there are many things that we haven't looked at. One big elephant in the room is that we haven't talked about at all the bias that the optimizer might bring into the picture and change the story. Maybe that changes the bound T naught and makes it much smaller, or changes the things in some way. And the last thing is that we showed procedures to be able to have length generalization in the last part for general hypothesis classes, but those procedures are far from being practical. So how to build methods that improve length generalization that can work for not just transformers, but any architecture. So maybe like I think a lot of the literature has focused on improving length generalization by building different positional encodings, but maybe there is a hope to uh, build different loss functions that might be giving you more robust length generalization. And yeah, that's the literally the last slide, and we can have any questions. I hope I'm still within the time limits, and there is a few minutes for discussion. If there are any questions, I'm happy to answer them.